The following video provides a short discussion on an ethical penetration test that was facilitated in the 2014 timeframe by a major financial customer. That customer has since moved ahead and deployed Avaya's Fabric Connect at several major locations. The customer in question wanted to validate our claims about the segmentation and security aspects of the circuit-based services within our Fabric technology. We were invited to participate in an ethical penetration test by the customer. Avaya agreed to the test and implemented the testbed environment with direct participation of the customer's staff. Avaya's SDN FX architecture is an approach that is based on our existing next-generation Fabric Connect solution, which is based on IEEE 802.1 AQ, or shortest path bridging. This foundation creates an automated Ethernet fabric core that is in turn leveraged by a higher-level open-source ecosystem, which is based on such consortiums as OpenStack, OpenFlow, OpenDaylight, and Open vSwitch. This development environment lends itself to a secure, enabled edge that allows for the extension of SDN services outside of the data center and to the users and devices. This approach is notably different than most other industry approaches, which are focused on the strict scope of the data center itself. Avaya's end-to-end fabric capabilities allow for the extension of next-generation SDN automation out to the edge, even in existing legacy or third-party networks. While SDN certainly has all of the potential necessary to bridge the agility gap, the existing implementations are far too short-sighted. To demonstrate, let's take a look at the three common SDN models: Open SDN, Legacy Automation, and Software-Centric SDN. Open SDN offers a plethora of tools to create an end-to-end solution and completely eliminates the complexity of the existing network by replacing it with white boxes. On the surface, we've met our requirements. Unfortunately, the story inside is not quite as appealing as the cover. While Open SDN is extremely powerful, it is also quite complex. The premise of white boxes for transport means that you simply are replacing your networking experts with expert coders who have to program flows of data and handling of that data across the infrastructure. The hardware still requires care and feeding as well, and the software still needs to be maintained. You likely will still have the same staffing constraints as before. Despite the potential increase in agility, you've gone from wrestling an alligator to holding a tiger by the tail, and networking security is the serpent around your legs and torso. Now, legacy automation, which is the second model, swings the pendulum back in the opposite direction. Rather than shifting the burden from the networkers to programmers, this model fully embraces the existing complexity. Not only does it embrace the existing complexity, it adds more layers of hardware and technology to automate that complexity. The real goal here is for customers to maintain their existing investments and vendors to further ingrain their lock-in, as it requires proprietary controllers and protocol interactions to gain what little benefit is realized by automating the core of the data center for VM mobility. Software-centric SDN is the final model, and it's a bit of a compromise between the two previous. It moves control of the paths for specific tasks up to administrators actually dealing with that function. So the premise of removing control from the networkers is similar to OpenSDN without requiring actual programmers to define things. However, the paths that are being created are done so on top of an existing network. Therefore, all the existing complexities and dependencies on network resiliency still exist without going as far as embracing and adding them to something like a legacy automation model. The biggest limitation that is shared there is that this model also focuses on virtual machine mobility across data centers only. Building your bridge on top of a marsh is bad enough, but the worst part is when you get to the other side and realize that there is no road to your final destination. Avaya's approach simplifies the underlying network by enabling an open, secure, simple automated core that lends itself to a secure software-defined network deployment. The real key is a true distributed control plane that, while still supporting separate control and data planes, allows for scale in both services density and services reach. The results of this are shown on the slide. A recent independent and anonymous customer survey has shown that the benefits of adopting Fabric Connect have been nothing less than phenomenal. In the past, services separation is often accomplished by both complex access control lists and route policies, or by the use of security appliances at multiple points throughout the network. While both of these technologies provide useful functions, when used at such levels within the enterprise, they result in complex provisioned environments that are not only prone to human error, but actually frustrate the automation efforts that SDN attempts to address because they are clumsy and lack ability. With Avaya's philosophy, the first step is to simplify the networking architecture by the introduction of Fabric Connect. This critical first phase introduces true secure virtual separation and inherent stealth security, which means that the paths and the topology of the fabric cannot be deduced from IP and port scanning or discovery methods. This phase also allows for the repurposing and condensation of security appliances and other technologies to well-defined demarcation zones. With the fabric serving as the foundation for the automated core, future steps allow for the extension of secure elastic zones that provide for the secure and proper placement of both devices and users into the respective secure zones, which we refer to as virtual service networks, or VSNs for short. The concept of elasticity can be viewed in two modes. The first is that of mobility at the wireless edge. Elastic secure zones can follow the user as they roam throughout the enterprise, thereby eliminating the need for complex tunnels and centralized controllers. The second is in the overall security of the network edge. As devices disassociate or disconnect from the network, the secure zone is retracted automatically. This assures that VSNs are always secure and never exposed by open ports at the edge of the network. This is the case not only for users and their typical devices, but also for the increasing number of pure devices that are the eyes, the ears, and the hands of the Internet of Things. As a result, these secure zones can be extended to protect things like video surveillance cameras, entry and exit controls, intelligent building systems, programmable logic controllers, such as those used in automated manufacturing, transportation, power grid management, oil and gas, and much more. The focus of the penetration test was to validate both the secure nature of these virtual service networks, but also the claims about their stealthy nature. Before we go into the details of the testbed, let's take a moment and talk about the anatomy of these circuit-based services. The anatomy of a Layer 3 stealth network is actually very simple. It's nothing more than an ISID, which is short for Individual Service ID, basically a shortest path bridging circuit, that is associated with VRFs. The VLANs attached to the VRFs are given IP addresses. However, none of the IP subnets are reachable outside of the IPVPN environment. As a result, a standalone Layer 3 IP internet is created where nothing can enter or exit. It is in essence invisible to the outside world. This type of service is useful for any secure Layer 3 protocol environment, such as those required for PCI DSS or HIPAA. But they are also useful to provide for service separation of possible conflicting protocol environments, such as those in the case of multiple multicast or application domains. The anatomy of a Layer 2 stealth network is also very simple. It is nothing more than an ISID that is associated with VLANs. The VLANs are not given IP addresses in this instance, however. As a result, a standalone Layer 2 network is created where nothing can enter or exit. These are extremely useful to extend secure Layer 2 protocol domains, such as those required for SCADA. Layer 2 stealth networks allow for the easy and secure distribution of such protocol requirements. Additionally, IP can run inside the Layer 2 stealth network. but it is a self-contained IP subnet that is not routed to the outside world. It is in essence invisible. As a result, it can be used for secure data center usage where IP reachability is not necessarily desirable. Finally, a comparable service in MPLS, known as VPLS, requires roughly 30 to 40 lines of code to execute, whereas a Layer 2 stealth network in Avaya's Fabric Connect is in essence one command. In the testbed environment, there were two secure zones created. The challenge was for the attackers to penetrate across from the green zone and infiltrate systems that resided in the blue zone. The test team was given direct membership to the green zone. In most attack or reconnaissance activities from the outside world, this would not be the case. Therefore, it was agreed that this would be a demonstration of an inside attack. Additionally, the attackers were given several IP addresses of systems that were hidden within the blue zone. Once again, this is not information that the typical attacker would have, and more appropriately illustrates an inside attack scenario. This is a quick illustration of the blue zone, which consisted of a single L3 VSN and several L2 VSNs associated with it. Once again, this was the target zone. The target systems consisted of a video surveillance management system, as well as dozens of IP-based video surveillance cameras. Going further, the complete system was running and totally dependent on IP multicast services provided for by the fabric. One particular thing to note is that we did not create a network with two secure zones supported on different nodes. In this lab, both secure zones were co-resident on the same Fabric Connect edges. This extension not only validates the secure nature of the virtual service networks themselves, but also the integrity of the topology, services, and forwarding databases within the Fabric Connect nodes themselves. This is the zone where the hacking team was given full access. As can be seen, it is very similar to the layout of the blue zone, and shares not only the same physical topology, but often the two zones are resident on the same switches. There were three focused tests. First, to demonstrate the stealth or invisible nature of Fabric Connect. The test should be unsuccessful to the typical IP and port scanning techniques. Second, to demonstrate the solid, secure segmentation between zones. And then third, to show the ease of configuration of the Fabric Connect switches. The focus of the Stealth Lab was to validate the invisibility of the network topology. Even authorized systems that have full access should not be able to determine the detailed topology of the network. A test was run on the current legacy IP-based network technology to determine the IP topology utilizing simple IP traceroute and port mapping utilities. As can be seen, the complete end-to-end path topology was uncovered. From there, the team was able to determine switch types, software code levels, and assured us that they could effectively draw out the network topology based on a series of these tests as shown, which they were soon able to do. Conversely, with the same methods, the team was unable to determine any topological insight into the Fabric Connect network, much less any of the switching elements involved in the topology. The network segmentation test was intended to validate complete network separation using the same physical infrastructure without the use of a firewall or access control list. In other words, this test was focused on validating of the Fabric Connect virtual service networks themselves. In the topology of the lab, there were two IP subnets used for this test, 10.120.0.0 and 10.140.0.0. Each subnet had two active IP service points within them. The team was given access to each subnet where they ran the Nmap utility to determine the number of active IP systems and then removed from access to one of the subnets involved. Here, the Nmap utility successfully discovers two IP service points in the 10.120.0.0 subnet that we have chosen to be visible. Secondary tests in the 10.140.0.0 subnet also yield two IP service points. However, when the team attempted to run the trace utility between the L2 IP VSNs, no topology information discovery was possible, further demonstrating that Fabric Connect is not dependent on IP path visibility to establish connections across the fabric. Note how that from the 140.0.0 subnet, none of the hosts on the 120 subnet are visible. The last lab focused on the use and ease of simplicity of setting up services within the testbed. The comparative legacy IP network, dozens of command line sequences were required in order to set up and deploy the required services to support the testbed environment. As can be seen, a ping utility was set up to ping an IP service point to the other end of the fabric. As you can also see, the ping is unsuccessful. The ping test will begin to return successful results once the end-to-end virtual service network is set up. Going into the configuration and orchestration manager, the network topology of the testbed is readily available. So while the IP hackers may be having a hard time deducing the actual topology of the network, the IT administrator always has a clear view. In this screenshot, the administrator is selecting the fabric nodes where the service is to be activated. With a simple pull-down menu interface, the L2 VSN is set up. In this instance, we are associating this L2 VSN with ISID 10,000. A simple save of the pop-up, and you're done. As a result of that very simple provisioning method, the IP subnet now has complete connectivity across the fabric. Focused objectives of this lab activity were met with flying colors. While this is a short snapshot of some of the testbed activities, there were many other tests and tools that will be used that cannot be disclosed due to intellectual property rights. Further, at no time were any of the IP addresses that we had chosen to hide become visible or discoverable by the attacker team. This further illustrates the ability of Avaya's Fabric Connect to selectively allow or disallow for both the visibility and reachability of IP networks in the fabric. As a result of this test activity, the customer is now deploying Fabric Connect at several major locations. From Avaya's larger SDN FX perspective, it's all about services separation and path control, or network segmentation, as referred to in various security documents. No other networking technology provides a more comprehensive set of services with so little complexity. As a result, the checklist is fairly easy. Be sure to terminate L3 VSNs as close to the edge as possible. Avoid using shared broadcast domains or VLAN extensions via tag trunks. If VLAN extensions from the VRF are required, use stealth L2 VSNs to maintain total separation. Limit port memberships into the security demarcation only to those who require it. Ideally, this should be a single port membership to prevent unauthorized access to the DMZ. Limit port memberships only to the required endpoints. Identity engines and Fabric Attach can greatly ease the enforcement of these access policies. Avoid mixing any non-secure applications in the secure stealth topology, even if they do not access anything outside the network, as such mixing can result in the violation of compliance. Validate the security demarcation and create defined security policy databases and network topology templates. Be sure to do testing of the demarcation to be sure that the policy database is enforced. Finally, avoid the use of the public internet in the end-to-end design. When this cannot be avoided, be sure to use encryption to protect transit data. MACsec or other methods of encryption can be used to protect exposed Ethernet trunks, and full VPN encryption can be used with IPsec or SSL to provide endpoint or even branch site connectivity. Be sure to have the VPN gateway attached directly to the stealth topology to ensure that there are no exposed unencrypted paths. While private IP VPN environments have been around for years, they are typically clumsy and difficult to provision. This is particularly true for environments where quick dynamic changes are required. As an example, the typical MPLS IPVPN provisioning instances will typically require approximately around 200 lines of command code, depending on the vendor and the actual service topology. Interestingly, much of this CLI activity is not provisioning MPLS itself, but provisioning other supporting protocols, such as interior gateway protocols and BGP. Additionally, consider that all of this is just for the initial service path. Any redundant service paths must then be manually configured as well. Compare with Avaya's Fabric Connect that can provide for the same service type with as little as a dozen commands. Additionally, there is no requirement to engineer and provision redundant service paths, as they are already provided by the intelligent fabric. As a result, IPVPNs can be provisioned in minutes and be very dynamically moved or extended according to requirements. An article on the evolution of E911 speaks to how an L3 VSN and IPVPN morphs over the duration of a given emergency. As an example, with different agencies and individuals coming into and out of the IPVPN environment on a fairly dynamic basis, based on their identity, role, and group associations. Furthermore, SPB nodes themselves are movable. Once again, ISIS provides for this feature. An SPB node can unplug from the network and move to the opposite end of the network topology, which can be hundreds or even thousands of kilometers away. There, they can plug back in, and ISIS will communicate the nodal topology information as well as all of the provision service instances on the node. The SPB network will in turn authorize and extend those services out to the node, thereby giving complete portability to that node as well as its resident secure services. In addition, SPB can provide separation for non-IP data environments as well. Protocols such as SCADA can enjoy an isolated non-IP environment by the use of stealth L2 VSNs. And further, they can be isolated so that there is simply no viable path into the environment for would-be hackers. This combination of privacy, fast mutability of both services and topology lend to what are termed as stealth network services. They are dark, so they cannot be seen or attacked due to the lack of surface for such an endeavor. They are swift in the way that they can morph by service extensions, and they are extremely mobile, therefore providing for the ability for nodes to make whole-scale changes to the topology and still be able to connect to their relevant provision services without the need to reconfigure anything. Any other IPVPN technology would be very hard-pressed to make such claims, if indeed they can make them at all. Avaya's Fabric Connect, based on 802.1aq, and SDN FX, sets the foundation for the true private cloud. With it, regulatory compliance and security becomes much, much easier. Thanks for your time. For more details on stealth networking technology, feel free to reach out to your local Avaya representative.